This video is going to go over the differences between ions, molecules, elements, and compounds. I'm going to start with compounds versus elements. Compounds are shown in the upper left-hand corner, and a compound is always composed of more than one element. There might be two, there might be three, there might be more than three. All of the compounds here are composed of two or three elements, but there can be more. So the different colors of the different spheres represent different elements. Oxygen is shown in red. That's almost always the color we use. Hydrogen, like usual, is shown in white, and carbon, like it usually is shown in black or dark gray, like you see here. Now, as opposed to contrast with that, elements in the lower right-hand corner are composed of only one type of element. Now, there might be more than one atom present, and so you see that helium, shown with the blue spheres, is a monatomic element. It exists as single atoms, as do all of the noble gases, helium, neon, argon, krypton, all of the ones in group 8A. Oxygen is diatomic. There are other examples of diatomic elements that we'll see. So here we have two oxygen atoms connected with a covalent bond. And S8 is a polyatomic form of sulfur, but all of these are elements because only one element is present, or we also would call them elemental forms. Now, if we look at molecules, molecules is a different idea. For a molecule, you have two or more atoms connected with covalent bonds. And so you can have molecules that are compounds that you see on the left, where there are at least two elements present, or molecules can be elements like you see on the right. And so all of these are examples of molecules. We have O2, N2, H2, those are all diatomic, and they are, we would call them molecular oxygen or molecular nitrogen or molecular hydrogen, or sometimes we just call them oxygen, nitrogen, and hydrogen. And then S8 is a polyatomic form of sulfur that we saw already, where there are 8 sulfur atoms connected to each other through covalent bonds. Now, many of the elements have multiple different forms. We call them allotropes, and so you may have, for example, ozone is O3. That's a different elemental form of oxygen that is not as stable as O2, which is what we would call molecular oxygen. O3, ozone, is also a molecule. It is also an element, and it is also an elemental form of oxygen. But it's not the most stable form. And we'll talk about stable forms much later in the semester. Here are some other diatomic elements. So hydrogen on the left-hand side primarily exists as H2 when it's in its elemental form, and as well as nitrogen, N2, oxygen, O2. And then all of the halogens that you see there, group 7A, those all exist in diatomic form. It's only showing fluorine, chlorine, bromine, and iodine, but astatine and the element below that would also exist in diatomic form. They're just not included here because they're radioactive, so they're so short-lived that they aren't easily studied, and so we often don't include those in our discussions. But like the other members of the family, they would behave in a similar way. This is meant to I wanted to talk a little bit about models, right? So we use a lot of models in class to sort of look at the shape of molecules. We use some three-dimensional models, and then these are just pictures of models. And so one type of model is called a ball and stick model. So you can see hydrogen chloride on the left-hand side. The ball and stick models on the top, each ball or sphere is an atom, and the stick represents the covalent bond. So that's a common representation of a molecule. Below that is called a space-filling model, and that is sort of meant to be a little bit more realistic image of what the molecule probably looks like, in the sense that the covalent bonds aren't really sort of accessible. If you are a molecule approaching this hydrogen chloride molecule and you wanted to interact with it in some way, maybe you wanted to come up and form some sort of bond with it, or you wanted to react with it, or you wanted to just interact with it, maybe you were attracted to it through some sort of intermolecular forces, which we'll talk about later. If you were another molecule looking at it, you would see what it looks like on the bottom, right? So the covalent bond is not something you could reach out and touch. It's something that is sort of obstructed by the size of the atoms that are there. I want to talk a little bit about ionic compounds. And so these are compounds in the sense that there are at least two elements present. For example, sodium chloride is the ionic compound that is shown here. Ionic compounds are not molecules. They are examples of compounds, but they are not atoms held together by covalent bonds. They are ions, so they're charged, and they are held together by ionic bonds. So an ionic bond is the mutual attraction of two opposite charges, as opposed to a covalent bond, which is the sharing of electrons. So if we look at an ionic compound a little bit more carefully, there's a sodium chloride crystal on the bottom that's just shown magnified. And then if you could put on your molecule glasses and magnify it many, many, many more times, you would see what you see in the with the green and the purple spheres. And one thing you can see is that the microscopic image that's sort of cubey shaped emulates or models or mirrors the macroscopic image of the cubic sort of structure. And that's often true. The microscopic crystal structure often mirrors the macroscopic image of the crystal as well. We look at sort of each of these compounds, each of these, so if you took different crystals, that's one of the differences between ionic compounds and molecular compounds, is that let's say we take a crystal of sodium chloride, just one little grain. Different size crystals will have different numbers of ions, and so the number of ions present in a crystal can vary. So maybe you take a crystal and it has 1,000 sodium ions, and it has 1,000 chloride ions. Or maybe you find a smaller crystal and it only has 100 sodium ions and 100 chloride ions. Or maybe you get a larger crystal and it has 1,000,000 sodium ions and 1,000,000 chloride ions. Now, a crystal that's the size you could see would actually have a whole lot more ions than that. It would be approaching Avogadro's number. But the point here is that there's not a set number of ions present in a given crystal, in a given sample. And so different samples are going to have different numbers of ions. So the numbers vary, but the ratio for sodium chloride, the ratio for any ionic compound is always the same. The ratio for sodium chloride is always 1:1. And we're going to talk more about that. But the reasoning is because the crystals have to be neutral in charge. And so since sodium is a +1 charge and chloride is a -1 charge, you have to have the same number of sodiums as chlorides, otherwise the crystal will not have a neutral charge. So that's the idea there, is that we're trying to balance the charges so that they have a 0 overall net charge. Now if we look at formation of sodium chloride, in the upper left-hand corner we have images of chlorine, which is the molecular form of chlorine. It's Cl2, and it is a greenish gas. On the bottom of that picture is a piece of sodium metal. Sodium is kind of a soft metal that is shiny, but it very quickly reacts with the oxygen in the air, and it tends to form sort of a makes it dull on the surface. The chlorine and the sodium will react with each other to form sodium chloride. Sodium chloride is the ionic compound that we just talked about on the last slide, where sodium is the positively charged cation and chloride is the negatively charged anion, and those two are held together with the ionic bonds, and that forms the solid sodium chloride salt that you see there. So on the bottom you see the balanced reaction where a sodium atom reacts with half a chlorine molecule, and the reason that that 1/2 is there is because you only need one chlorine atom to form one formula unit of sodium chloride, and so we put a 1/2 there to make that balanced. Another way to have a balanced reaction here would be to have two sodiums, one Cl2 molecule, two sodium ions, and two chloride ions. But in this case, this is just a simpler way of writing the reaction. We're going to talk soon about why sodium would want to give its electron away to chlorine. And so that's what's happening here, is sodium atom is giving away its one valence electron to chlorine's atom, and when chlorine takes that valence electron, each of them has a complete octet, and that's what we're going to talk about very soon. We're going to talk about electron configurations of ions. Now, there is an earlier video that describes electron configurations of atoms, and how you would use the periodic table to write electron configurations of atoms. So if you don't remember how to do electron configurations, then that's a video you should probably go back to for review. So we're going to assume that you already know how to do that. So if we compare the neutral atom, or just the neutral element, to its most stable ion, we'll start with sodium. Sodium is an alkali metal. It's here on the periodic table, right? And so its electron configuration, if we start with the inner core, is going to be 1s2, 2s2, 2p6 all the way to neon, and then 3s1. So its one valence electron will be in a 3s orbital. So we're going to write that down. And then when it loses, so it's preceding, so you can write down the complete electron configuration, 1s2, 2s2, 2p6, 3s1. Or if you want to use the abbreviated electron configuration, this neon is the preceding noble gas, and so you would write down neon in brackets, and then you'd write 3s1. So this is the abbreviated electron configuration for neutral sodium atom. Now when sodium loses its single valence electron, it's going to lose it from the 3s orbital. So sodium plus 1 is going to have the noble gas, neon noble gas electron configuration, which is very stable. We have learned, right, that noble gas configuration is unusually stable. This is why sodium's predominant, most stable form is sodium plus 1 cation. Calcium, if we look down here, calcium is element 20. The preceding noble gas is argon. So calcium's valence electrons are in the fourth shell. Argon 4s2 is its noble gas, is its electron configuration for calcium, neutral calcium atom. Calcium loses 2 electrons to form calcium plus 2 cation, and the reason it does that is because it then gets the noble gas configuration of argon. Now if we look at chlorine, neutral chlorine is element 17. It is here. Its preceding noble gas is neon. So we're going to write down, and this is the 3p, so 3s2, 3p, 1, 2, 3, 4, 5. So its neutral chlorine atom has this electron configuration with neon in brackets 3s2, 3p5. Chlorine tends to gain electrons. It gains 1 electron to form chloride ion, as do all of the halogens. So to form chloride, we end up with neon 3s2, 3p6, which is the same as the next noble gas configuration, which is argon. And so this helps us understand why chlorine would be chloride, would form chloride. Now next we're going to move on to oxygen. Oxygen is element 8. The preceding noble gas is helium. So we're going to write helium 2s2, 2p, 1, 2, 3, 4. So 2s2, 2p4, and it loses, oxygen gains 2 electrons to form oxide ion, and that's going to give it helium 2s2, 2p6, which is the same as neon's electron configuration. And so now what you can see is that elements tend to gain or lose electrons to complete an octet. And so they either, if they only have 1 or 2 to lose to get a full valence shell, then they will lose those. The metals tend to do that. And the nonmetals, because they only have 1 or 2 to gain, they tend to gain electrons to form a complete octet. So this table shows you electron configurations. We're going to come back to this. We talked about this in the next video talks about this a little bit more, but here we have group 1, group 2, group 3. These are all metals. They tend to lose electrons to form cations, and they obtain these electron configurations, which are all noble gas configurations. And here we see group 6 and group 7 which tend to gain 2 and 1 electron respectively, and that also helps them achieve noble gas configuration. So this helps us understand why group 1 is +1, group 2 is +2, group 3 is +3, group 7A is -1, and group 6A is -2. Hydrogen is unusual. Hydrogen can either gain 1 electron to form hydride, or it can lose 1 electron to form H+. Either way, if it loses 1, it has no electrons, and if it gains an electron, it has a full 1s shell, right? So either way, it is stable. So hydrogen actually has 2 different sort of ways it can exist. Now, if we look a little more closely at our formation of sodium chloride that we looked at a few minutes ago, then this is the same reaction that we saw earlier on the top. And there's going to be an electron transfer that occurs between the sodium atom and the chlorine atom to form sodium cation and chloride anion. And so you see the electron configurations on the bottom, and now we understand that sodium really doesn't want this valence electron because it's not stable with that single electron in the valence shell. So if it can give that electron away, and chlorine is there, and chlorine is just desperate to have an electron because that would allow him to have a full valence shell. And so when you bring these two together, since one of them is happy to give away an electron and the other one is happy to take an electron, it's like a win-win situation where they both form a more stable product, sodium cation and chloride anion. And because they are mutually attracted to each other, they immediately form an ionic bond and form sodium chloride. So this reaction is very fast, very energetic, occurs very easily whenever you put sodium metal in the presence of chlorine gas. And here this is just explaining that a single valence electron will get transferred to chlorine to form chloride, and we form a much more stable set of products. It's a win-win. Both have a complete valence shell, and then they form a mutual attraction, the ionic bond, which occurs very quickly.